Hi, this is Hyunjun Jang, and today we will review a NIPS tutorial, Adversarial Robustness, Theory and Practice. Our team members are Dong-hoon Lee, Hyung-woo Park, and Hyunjun Jang. Okay, let's start. Adversarial examples are visually indistinguishable from normal examples, but specifically tuned or optimized to fool or mislead the machine learning system. Let's consider the user training process we have done. We have model parameter theta, and input x, and corresponding label y. We learn the model to minimize the loss, which defined by theta and x and y. After learning converge, we use this model to infer the label of unseen example. However, it is known that these normal models are easily fooled by adversarial example. Obtaining adversarial examples is an optimization problem itself. Here, we have delta, which denotes the perturbation to be applied to an image. The optimize to maximize the loss over correct label over data. After few iterations, we obtain delta that fools the model output, but visually indistinguishable. We usually call this as adversarial attack. Not only adding specific noise to the image, but you can also fool the classifier by making changes in the real world. In practice, the physical changes also affect the performance of the classifier. For example, in the right figure, there is a lifer, and the label predicted by the classifier is varied depending on the angle of the image. It does not add any specific noise to the image, it only adjusts the viewpoint. So, rotation or translation suffice to fool the state-of-the-art vision models. Generally, when we train a classifier, we use data augmentation, which are using rotation and translation. However, as you can see in this example, this does not seem to help for adversarial examples. There is another problem in normal classifier. It is data poisoning. The goal of data poisoning is maintaining training accuracy but hamper the generalization. If we manipulate the small fraction of image, it can maintain training loss to be small, but it tries to hamper generalization. If we just change just tiny fraction of the dataset to essentially take full control over the classifier, it will affect the performance of classifier. For example, in the left figure, we add some specific noise, and it leads the classifier to predict the image as fish instead of dog. Another data poisoning method is it just plants an undetectable backdoor that leads the classifier to predict the image as some specific label. For example, in the right figure, just plant some small backdoor on the right upper side, then the classifier predicts the image as different label because of the backdoor. This situation is a big problem for applying machine learning to autonomous driving or robotic control or such other real environment. So in this tutorial, we will discuss about how these adversarial examples came from and how to learn an adversarial robust classifier. What we're trying to do when we do training is essentially finding a setting of parameter theta that minimize the loss on our training examples. Our models are differentiable in this parameter theta, so we can use gradient descent to find the good setting of theta. Unfortunately, this is also like the fact that deep learning networks are also so convenient to optimize in various shapes, and the form is also can be applied adversarial perturbations. However, there is an important setting for delta. In principle, delta should be small because if delta is large, so it can really change the label of image, and the classifier predict it as different label, and it is just we want it. So delta should be small with respect to some LP norm and rotation and translation or rigid feature perturbations. So let's discuss about how adversarial exams came from and their verification. We want to train a model that is well generalization as well, not just on fixed dataset, but actually on adversarial perturbations of the dataset. We are going to minimize this objective overall. This objective function consists of two portions. First one is inner maximization, which is finding adversarial examples or verifying that cannot exist adversarial examples. And second portion is outer maximization, which is training a robust classifier against adversarial examples. So let's see how the adversarial examples come from. The left figure shows the loss landscape. So we have some perturbation region delta that's shown on the bottom there. We have some initial point delta 0, and we have some loss function that exists for different perturbation delta. And now we want to maximize this quantity. There are three options to do that. The first is we can do local search. It just to sort of search to find an adversarial examples, and this is actually the most common thing that's done in practice, and this is sort of what people typically talk about adversarial examples. And the second thing is combinatorial optimization, which is for small model. It is to actually solve this problem exactly using techniques and combinatorial optimization, so we can find the actual worst case example for a given classifier. And finally, we can also form an upper bound on this loss function, at least over the region of delta. And this upper bound has a properties that is convex or concave. And we maximizing it, we can actually find exact solutions as well. Then we'll also give verification of whether or not an adversarial examples exist or not. The most loss landscape of deep learning is non-convex and find local optima. So it is difficult to find that exact solution to maximize the loss. So here we try to solve this problem by using gradient descent just to find an approximate solution. So recall that we want to maximize the loss using perturbation delta. We want to optimize our perturbation bound in some region delta that's represented by gray region. And we just take a step in the direction of gradient of the loss function. So we are taking a pulse up in the positive direction because we are trying to maximize the loss function. And then we just project back onto the set, so we find the closest point in the set to our projected point. And we just repeat this process to find the highest cost. The fast gradient sign method, FGSM, is a particular type of attack which using projected gradient descent. Let perturbation region delta be an infinite ball and each norm is less than small value epsilon. In this case, actually projection is very easy. For some given example x, we know that we are going to adjust delta in the direction of each gradient. In order to maximize the loss, we want to adjust delta in the direction of this gradient. As I mentioned before, projecting delta on this number simply involves clipping value of delta to lie within the range minus epsilon and epsilon. And if our initial delta is 0, this gives the update as clipping delta to minus epsilon and epsilon. And if we want to increase the loss as much as possible, we try to increase the step size of alpha. And in this case, if we take alpha to be very large, we will simply take delta to be either plus epsilon or minus epsilon, depending upon the sign of gradient. This is called fast gradient sign method. In here, we illustrate the result of FGSM method. We use two-layer fully connected multilayer perceptron and 6-layer convolutional networks and used MNIST dataset. So let's see FGSM actually do. And the given image indicates 7. After using FGSM method, these models misclassify the image as label 3. Let's look at the actual test error of these things. On clean accuracy, these things both do quite well, and when you run this attack method, you get a very large error for both things. FGSM is quite a simple algorithm, so we can further improve it. The next step is just to actually run the fine-grained project gradient descent method rather than taking sort of one big step. In the right figure, in the first point of gradient point in the top right corner, however, after some iteration, the gradient points the top left corner, so it means the delta that makes the loss highest is not top right corner, but the top left corner. In this method, you just take a small gradient step and iteratively update your delta in the range of large delta. This is called projected gradient method, and it is much slower than FGSM, but typically able to find better optima. In here, we illustrated the result of PGD method. The projected gradient descent doesn't look that different actually. Both methods fool the classifier 7 to 3. But if you look at the actual test error, there is quite a big difference here. FGSM fools 41% of the examples on convolutional network, whereas projected gradient descent improves that quite a bit. So far, we saw that we just maximize the loss of classifier, but we can actually maximize the loss of true class and minimize the loss of target class to try to fool the classifier into thinking it's actually a target class. The loss function is something like the cross entropy loss. Then, the difference of two of these loss functions, the first term, the normalization term, actually cancels. And so the actual target attack is the same as just maximizing the difference in the class logic. So the last formulation is actually equivalent to doing that. So let's see the targeted attack examples. In above direction, we maximize the linear term of 0 class minus linear term of 7 class. And we get the 0 prediction. And if we change the target class as 2, then we can get the prediction as 2. In particular, we actually can solve inner maximization problem using combinatorial optimization. In here, we actually don't exactly solve the inner maximization problem in the multi-class case, but we can determine exactly whether or not an adversarial example exists within a certain radius. We can write our network, and explicitly we have a multilayer ReLU network. Let's say Z indicates the linear function's output of previous layer, and HB a class logic. And now we can actually write the targeted attack as an optimization problem. The idea is we are going to minimize the inner product between unit basis on the true class minus the unit basis on target class and multiply class logics. So again, all we are really doing here is we are minimizing the class logic of the true class and maximizing the class logic of target class. This is subjected into ReLU constraints. The problem here is that this ReLU operation is not convex constraint, nor is natively handled by most optimization solvers. In order to solve this problem, we need to convert it into alternative form, specifically a mixed integer linear program. A binary mixed integer linear program is an optimization problem that consists of linear objective and binary constraints on some of the variables. In practice, these solvers can scale hundreds of hidden units, but it depends heavily on the problem structure, so it only can be applied small network and give us what's the worst you could do on any given task. And one of key aspects of finding an efficient solution is to provide linear bound on the prevalue activations. One question remains for the integer programming formulation is, how do we find the upper and lower bounds? Mathematically, this doesn't actually matter, but the solution time of integer programming solvers will depend heavily upon having a good upper and lower bounds. We can actually compute the exact value of these bounds precisely the same way as we compute targeted attack. We could compute an upper or lower bound by minimizing the single activation value at an intermediate layer. While this would be an exact solution to the upper and lower bounds, it is extremely impractical, owing to the fact that we are essentially solving two integer programming problems for each hidden unit in the network. So, it is much more practical to simply choose a set of much looser bounds that are very fast to compute. One natural choice to compute fast is to use simple interval bounds. If we have some bounds on Z, then the question is how large or small could we make the term WZ plus B? Let's consider a single entry WZ plus B. If we want to minimize this term, and whenever an entry of W is negative, we should choose Z as upper bound, and whenever W is positive, we should choose Z as lower bound to minimize the term WZ plus B, and vice versa. Let's see below figure. We are propagating intervals to the network, so if we just run the point to the network, it produces some output. But if you actually think about a region around the point, that the region will similarly propagate the network and really typically grows in size as it goes to the network. That's all we are doing here. We are forming these interval bounds to kind of show what sort of regions you can achieve with classifiers. Let's discuss more this in convex relaxation part. We can use bound propagation to certify robustness of classifier. We are trying to minimize the class logic of the true class and maximize the class logic of the other class. So, if we solve this problem and the result is negative, that means the target class's activation is higher than the truth class, and this means we have an adversarial example. On the other hand, if we solve the same thing and the objective value is positive, this means there is no adversarial examples because the class probability of true class is still higher than the probability of the target class. So, if we have a 7 image here, and say we solve some problem and trying to have a targeted attack on the class 0, and the result is negative, this means that we have an adversarial example. Whereas, if we do something like this to target class 1, the result is positive, that means there is no adversarial example. Finally, to solve the inner maximization problem, there is convex relaxation method. While the exact solution to the inner maximization problem based upon integer programming is valuable, the approach does not scale to substantially larger networks. Because of this, we need to obtain fast upper bounds on the inner maximization problem. In previous approach, we used ReLU operation and it is not convex set and hence hard to optimize over it. We would have a linear program for which there exists very fast solution method. Now what we can do instead is replace the non-convex set with its convex relaxation, which means that the next layer and the previous layer, they don't lie on the ReLU anymore. They now lie within some relaxed linear set. If you take the known ball and sort of feed it through the network, the first figure shows kind of some complex shape, and what we are doing effectively is we are relaxing the shape about an outer bound on the shape, which gives us more freedom to choose adversarial examples. The objective of targeted attack for the linear program is gonna be actually a lower bound on objective of truthing. Solving a linear program is still quite slow, so we need to find some technique to do fast. By using linear programming duality, it is possible to achieve a lower bound on the linear programming via backboard path through the network. But it is still quite slow, and there exists a method that's fast and competitive. It is interval-based bound. It turns out if you sort of take those interval bounds, we now have a known region the last layer of the network can lie in. In previous slide, we used interval-based bounds, which provide a loose relaxation of problem. In here, however, we will provide even looser relaxation of the problem because it is currently convex relaxed. Suppose we solve our verification problem using the binary integer programming formulation. If the result gives us a negative solution, it means there exists adversarial example. On the other hand, if we do the same thing with the convex constraints, we also get a negative number because it is convexly relaxed. However, in here, we cannot know anything about whether there exist adversarial examples or not, because we relax the set of activations and negative number is result of relaxed set, not our set. However, if the result is positive number, then we can certify that there is no adversarial example to make classifier to predict to target class. And until now, we covered the techniques we have for dealing with that inner maximization problem. And now, Hyung-woo will present training adversarial robust models and their analysis.
Okay, now we'll talk about training adversarially robust model. So let's take back to the previous big picture. In the previous chapter, we focused on creating adversarial examples. It means how do I solve the inner maximization problem. Well, part 2 is going to be about how do I train the model that somehow is robust to these adversarial attacks. The strategy for creating adversarial examples that we mentioned lead to methods for training robust model. We focus on methods for solving inner maximization problem of a perturbation, that is to finding the solution to the following problems. We have mentioned some strategies for inner maximization problem, and it is for creating adversarial examples. First, using our local bounds naturally lead to procedure that we call adversarial training. Second, we cannot use conventional optimization for training adversarial robust model. It has large computations for it. Third, we can train models based on convex relaxation, and this will lead to probably robust model. So, first of all, we will start talking about adversarial training. The basic idea is to simple. Create and then incorporate adversarial examples into the training process. Since we know that standard training creates networks that are susceptible to adversary examples, let's just also train on a few adversarial examples. Now we would like to able to optimize this with gradient descent. But how do I take the gradient of this term when it involves max term inside? How do we go about computing this inner gradient? It can be solved by Daskin's theorem. So idea here is very simple and intuitive, but it actually have a very subtle point is that if I want to take a gradient of this max term, what I can do is to find the optimum over the set and take the gradient at that optimum point. In other words, let the delta star denote the optimum of the inner optimization problem. Then the gradient we require is simply given by this. It is actually a subtle point, and it is not trivial to show that this holds. We don't prove Danskin's theorem here, just note this property in this slide. So let me start. We will start talking about adversarial training advocated by Ian Goodfellow. The idea is simple. Instead of training at the actual data point, you train at the worst case perturbation of those data points. So first, select mini-batch B. For each B, solve the inner maximization problem. In other words, we find the worst case perturbation. Then update parameters based upon the gradients at those worst case perturbations. We iteratively compute adversarial examples and then update the classifier based upon original data, but also these adversarial examples. That's actually all this model do in this adversarial training process. This is one of the most effective empirical methods for training adversarially robust model. So we had a company which trained with normal training and it did really well on standard adder here, but it actually did it worse when we attack with the FGSM or PGD. It does much worse. So if I train my same exact architecture using this adversarial training method on the right here, we actually get a much more robust network. So next, let's use the convex bound. In this case, we are gonna use those interval bound based approach to see what level of adversarial performance we can guarantee for the robust model. As shown in previous slide, the model improves error rate for FGSM and PGD, but unfortunately, the extra robust bounds you get if you run convex procedure for both these things is completely vacuous. It's totally vacuous here. So what's going on here? The key insight here is that models can be convexly verified to be robust are a small set of what seem to be the actually robust models. You can think of a Venn diagram here. There's all models and putting on robust ones. There's some spaces robust models in that, and then within that there's some space of convexly verifiable models. It turns out that this convex bound, tractable probable bound that we have are very loose, unless the model is built specifically with them in mind. So it's great that we have these bounds, but in order to get them say anything non-vacuous about classifiers, we actually need to train models upon them. Convex bounds are just a differentiable function of network parameters, and what that means is that a finer convex bound that we have and these things is also a differentiable function of the model parameters. So what can you need to actually minimize not our actual robust loss? That's very hard things. So but to minimize a strict probable upper bound on the robust loss of classifiers. Recent work surprisingly shows that interval-bound propagation actually can sometimes work better for this than more complex approaches. The result shows test error also. The attacks of the different things such as FGSM, PGD, and probable bound. The standard component gets bad in all adversarial attacks. Robust component trained with PGD works well in some attacks, but the bound itself is completely vacuous. Finally, if I train the network to minimize this bound, we get this good result. Now we will talk about machine learning via robustness aspects. We will see how does machine learning look like to these lenses of robustness. So, how does adversarial robust machine learning differ from standard machine learning? On the mathematical level, all that we are trying to compare is these two fields. Standard machine learning tries to minimize the risk, and adversarial robust machine learning tries to minimize the risk for adversary example. What does change when we move from standard machine learning to the adversarial robust machine learning? The first one is just about overfitting of robust deep learning. Over here, you can train some classifier, and this is the training accuracy. So after running for long enough, we can get 100% training accuracy. The accuracy we focus on is for the unseen test set, and this is the user performance we observe. The gap between what we can ensure by training and what we actually also get on unseen samples, the generalization gap tends to be really small. This is great in the standard machine learning, but how does it look like in robust machine learning? In robust setting, it's much harder to get 100% robust training accuracy, or even impossible because of data being not perfect. So there exists a classifier that is robust. However, if you look what happens on unseen examples, that's the performance we observe. So we have this really huge generalization gap in robust model. In this situation, what can we do? The obvious idea that we know is just to use regularization, but it did not help either. They discovered some phenomenon that actually turns out that if you think about aiming for adversarial robust generalization as opposed to standard generalization, then actually it's not only a matter of optimization problem corresponding to training becoming more difficult, but also a matter of sample complexity of this problem. Especially, it tends to need more data to even be able to get a robust classifier. So here is a theorem. Sample complexity of adversarial robust generalization can be significantly larger than that of standard generalization. So here's another issue. How does being robust affect our standard generalization? If we get a robust classifier, then it should be superior to standard classifier in all aspects. In particular, we know that one of the effective techniques to get a better standard generalization is data augmentation, which is adding some transformation to training data during training. If you look at adversarial training, which is current leading technique to get robustness, you can view it as a ultimate version of the data augmentation because it trains on the other side perturbation of the training data. And so in some ways, you are training on the most confusing version of training set. Then being robust can make standard generalization even better because we can think adversarial example is the ultimate version of the data augmentation. So in this slide, there is standard test accuracy graph. This is just a reference point. However, if we take a look at what happens if we look at the standard accuracy of the robust model, then we see that there actually is a gap. It's not a big gap, but it has a gap. At the end, it's always consistently lower than standard training. So where is this gap coming from? Why is this robust model inferior than the standard training? So first of all, if I trying to train a classifier, I have to choose if I want to maximize this standard generalization performance or I want the classifier to be robust. And that is actually an inherent trade-off between this. You can imagine the dataset in which first coordinate is strongly correlated to the correct label, but it's not perfect. And then we have bunch of very weakly correlated features. What will happen in this correlated features? If I aggregate them, they will be aggregated to meaningful meta feature. But the problem is that in standard training, you will just use meta feature to get essentially perfect classification for improving performance. However, in the robust setting, you are not able to take advantage of these features because even though they are very accurate on average, they are very easy to be manipulated by adversaries because each one of them is weakly correlated with the correct label. So we summarize where we are. We think about differences between standard machine learning and standard machine learning. No, we think about differences between standard machine learning and robust machine learning. There actually exists a price to be robust. In particular, first, optimization problem we need to solve during training is way more difficult and models need to be a little larger. Also, we just mentioned that actually you might also need more data set when you train robust model. And finally, you might give up a bit performance on standard accuracy. But there are some unexpected benefits beyond just being robust. It turns out that robust models tend to be more semantically meaningful. As shown in figures, what they discover is that we can get this lineage map from gradient of adversarial robust model, and it's more semantically meaningful than gradient of standard model from this input. This is some unexpected benefits of the adversarial robust model. Thank you.